Hi and welcome to my third video in the series about blood transport, and today we're looking at blood pressure and velocities. And so if you've ever had your blood pressure taken, you probably know that there's two numbers attached to it. And so the systolic blood pressure is basically the pressure produced when the heart is contracting, and the diastolic is the pressure produced when the heart is relaxing. And so what you can expect is the diastolic obviously to be much higher than the systolic to be much higher than the diastolic. And so when you get your reading, you might have had one done, and so a typical reading for a man might be 120/80, and so 120 represents the systolic and the 80 represents the diastolic. And so this diagram here gives us an explanation of what happens to the pressure as you go further away from the heart. So as the blood leaves the heart, it leaves under high systolic pressure. And so as you move further away from the heart, it has less resistance. And so the friction within the vessels reduces the pressure of the blood. And so eventually there's no systolic or diastolic pressure, but a smooth, constant flow. And so if you looked at the pressure within an artery, particularly if you looked at the aorta, you'd see that it has periods of high pressure and then slightly reduced. Obviously once you get to veins, where there's a smooth, constant flow, you don't have the pressure of the systolic and diastolic. And so what we can look at in terms of the blood vessels, we can look at what the pressure's like between them. And so if you have a look at the ones with the highest pressure, that would be the arteries, then the arterioles, then the capillaries, and then obviously we can insert the venules here, and then finally the veins. So what this is showing is the further distance away from the heart, then the pressure goes down essentially. And if you look at the difference between an artery and say a vein, an artery is a very thick elastic tissue and muscular tissue, and so it can withstand high pressure. The vein, a bigger lumen, so it produces less friction and also has a much less pronounced elastic layer, and because it doesn't require it. So if we looked at a diagram showing the pressure between the different blood vessels and then showing the overall pressure of those, you can see that the aorta is the major blood vessel coming out of the heart, or the major artery coming out of the heart, and so you can see it has not only systolic but diastolic pressure. And you can see as you go further away from the heart going towards the veins, then the pressure drops dramatically from those. Obviously once you get to roughly around the capillaries, there's no more diastolic or systolic pressure, and so that idea of having the pressure exerted from when the heart is contracting and relaxing is only relevant to arteries and arterioles. And so we also look at how quickly the blood moves through these different blood vessels, and so that's referred to as blood velocities. And you can see here there's a diagram showing essentially the velocity of the blood through these different blood vessels, and so what we're going from is the one closest to the heart, so the aorta and the arteries, and then the one returning to the heart, which is the vena cava. And what you can see here, the relationship here is in the arteries, it tends to be very quick. So the closer it is within the arteries to the heart, then the quicker it moves through. The actual point at which it moves the slowest is through the capillaries. Now the reason for that is because it's got such a big surface area. And so if you look at this line here, this illustrates the total surface area of these sections. And so what you notice is the capillaries have such a huge surface area, and so what's happening is the blood is being funneled through these different channels, and so it's slowing down. So a bit like at a junction where loads of cars, and if you've got a junction where loads of cars can peel off, then the overall speed tends to go down. And you want that at the capillaries because the capillaries are the site of exchange, and therefore you want them to be going slowest through there, so you can allow the maximum time for diffusion and for exchange of different materials. What you tend to find is it picks up speed through the veins, and then when the vena cava tends to go reasonably quickly back to the heart. But you can probably see here there is a relationship between the total surface area of a specific type of blood vessel and then the velocity. Generally speaking, the lower the total area, or the area of the total blood vessel, the higher the velocity. And so as the total area increases, you can see the velocity slows down. And so that's a good way to think about this. And so the final thing that we have to look at on this video is how carbon dioxide is transported through the blood. So you're probably aware that oxygen is carried on the red blood cells and combines with the haemoglobin, but carbon dioxide is slightly different. And so there are three major ways in which it's carried. So 7% of it is carried in the blood plasma, and so not associated with the red blood cell. 23% is combined with haemoglobin, and so it's carried on the red blood cell, and the remaining 70% is transported as bicarbonate or hydrogen carbonate ions. You're probably aware that you might have cooked with bicarbonate of soda, and so bicarb is actually used in recipes to release CO2. So you use it in cakes, and so this releases the CO2 and actually forms bubbles and gives you a lighter cake or a sponge. And so most of your carbon dioxide is actually carried as bicarbonate, and so therefore can have an effect on the blood systems, and specifically what we look at in the next video, your oxygen dissociation curve.